Okay, so 5.3 is on the divergence test. And integral test. So we're looking at series and we're saying, hey, does this series converge? Does this series diverge? We're going to use the divergence test to say, hey, this thing diverges. And we're going to use the integral test to say, hey, this thing converges or this thing diverges. So the divergence test is not a convergence test. It is a divergence test. Okay, so last time we had said that, if the limit goes to 0, then that was not a convergence test because of the harmonic, right? So the last time we said that if the limit as n goes to infinity of, or n goes to infinity of a sub n, if that did not go to 0, sorry, last time we said that if it did go to 0, sorry, then this does not prove convergence. However, the opposite is true. If a series is convergent,
Convergent is an adjective for things.
I have to turn my cell phone on. Okay. So if the series is convergent, then the limit as n goes to infinity of a sub n is equal to 0. So if it is convergent, then it goes to 0. Okay, so everything that's convergent, the limit goes to 0. So if you were to look at like a Venn diagram here, we would say, if it's convergent, then the limit as a sub n, as n goes to infinity, is equal to 0, right? So, but there are things like the harmonic series that are outside of convergence. Okay, so the contrapositive of this statement is also true, okay, in that if the limit as a sub n, as n goes to infinity, is not equal to 0, then then the series is divergent. I can't have a convergent series where this does not go to 0. Okay, if it doesn't go to 0, then the series is divergent. This is a test for divergence only. Okay, a counterexample is the harmonic series. Okay, where a sub n is equal to 1 over n, where we have the limit as n goes to infinity of 1 over n is equal to 0, which tells us nothing. Okay, it is divergent, but that goes to 0. However, if the limit does not go to 0 of the terms, if the terms are not getting smaller, then we keep adding bigger and bigger stuff, or we keep adding the same stuff, the thing's never going to converge. It's just going to diverge. So if it does not go to 0, if the terms do not go to 0, This is also called the nth term test. This is the divergence or nth term test. Okay. Okay, and formally it says that if the limit as n goes to infinity of a sub n does not exist, or the limit as n goes to infinity of a sub n is not equal to 0, then the series summation n equals 1, we'll start at 1, n equals 1 to infinity of a sub n, is divergent. It is divergent. So that's the divergence test or the nth term test, called the nth term test. Didn't write that too well. Nth term test. Or the divergence test. Okay. So it just says, hey, if the terms are not getting smaller and going to 0, then the series increases to infinity. Then the series increases. Okay, number 1. Show that the series summation n equals 1 to infinity of n squared over 5n squared plus 4 diverges. Okay. So I want to look at the nth term, the limit as n goes to infinity of n squared over 5n squared plus 4. I'm going to use L'Hopital's rule on this. So the limit as n goes to infinity of 2n over 10n, n's cancel, I'm just left with 1/5. Which is not equal to 0. It just says that, hey, you're going to end up adding 1/5 forever. And if I keep adding 1/5 forever, then, if I keep adding 1/5 forever, then it's not going to get smaller. It's just going to blow up and it's going to diverge. Thus, by the divergence test, the series diverges. Let's look at a theorem. If the series a sub n and the series b sub n are a convergent series, then so are a constant times a sub n, a sub n plus b sub n, the series of a sub n plus b sub n, and the series of a sub n minus b sub n. So we can subtract the series, add the series. If or multiply the series by a constant, and it does not change its convergency. Okay, its convergent nature. Okay, the integral test. Suppose f is a continuous positive decreasing function on 1 to infinity, and let a sub n equal f of n. Then the series n equals 1 to infinity of a sub n is convergent if and only if the integral of 1 to infinity of f of x dx is convergent. Convergent. That is, if the integral 1 to infinity of f of x dx is convergent, then the summation of a sub n equals 1 to infinity, is also convergent if the integral 1 to infinity of f of x dx is divergent, then the summation n equals 1 to infinity of a sub n is also divergent. Okay, so whereas the divergence test was just a test for divergence, this is a test for convergence or divergence. Okay, so if we take the integral of the function that we're working with, the a sub n that we're working with, we take the integral from 1 to infinity, and we add all that up, and it goes to a value, then it converges. If it doesn't exist, if the integral does not exist, or it goes off to infinity, then it is divergent. Okay, number 2. Test the series okay, n equals 1 to infinity of 1 over n squared plus 1 for convergence or divergence. Okay, the integral 1 to infinity of 1 over x squared plus 1. So we're taking the function, the a sub n, we're turning into a function of x, and we're integrating from 1 to infinity. Well, this guy here is the integral of 1 over x squared plus 1. That's the inverse tangent function. So that's the inverse tangent, okay, of x from 1 to t, where the limit as t goes to infinity. Okay. So this becomes the limit as t goes to infinity of the inverse tangent of t minus the inverse tangent of 1. So what does the inverse tangent of t look like as t goes to infinity, as we let this go bigger and bigger? Well, the inverse tangent looks like this, and it has some asymptotes, okay, and it's at pi over 2, and the other asymptote here is at negative pi over 2. Okay, but as x goes to infinity, okay, or in this case t, as t goes to infinity, this thing is going to get closer and closer and closer to pi over 2. So the limit is pi over 2. Okay, so this guy, okay, is pi over 2. Let me bring this down. Okay, let's bring this down. This is pi over 2 minus. Now, what's the inverse tangent of 1? The inverse tangent of 1? It's pi over 4, right? Okay, so I get pi over 2 minus pi over 4, which ends up being pi over 4. Okay, oh, okay, pi over 4. Okay, which is a value. It's a convergent value. So, okay, thus, since the integral 1 to infinity of 1 over x squared plus 1 equals pi over 4, okay, and converges, the series summation n equals 1 to infinity of 1 over n squared plus 1 also converges. Okay, so this is convergent by the integral test. Okay, on the exam, I would like you to tell me which test you used. Okay, at the very end, like, oh, this is by limit comparison test, or this is by, alternating series test, or this is by integral test, or this is by whatever it is, whatever test you're using. Okay, I want you to tell me that test. If it's divergence test or geometric series test. Okay, so we have three of them. We have four of them actually so far. Okay, we have geometric test, we have a harmonic series, we have divergence test, and we have the integral test. So we have four. We're going to end up with 10 tests total. And I'll give you a printout of all 10 tests so that you have that for the exam. But I want you to tell me at the very end what test. If we forget to mention how many points will we lose, I don't know, one or two. So it depends on how many questions there are on, how much points. If it was worth 10 points, then you probably lose 2 points. Okay, if it's worth 8 points, maybe one point. If it's worth 12 points, maybe 3 points. So you're going to sit there right up in the, basically you're going to knock yourself from, 100% down to 80% if you forget to tell me the test. Does that help? Okay. 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 Okay, P series. So this is the next test that we're going to look at is the P series test. Okay. The P series the P series, okay, summation n equals 1 to infinity of 1 over n to the p power is convergent for p greater than 1 and is divergent for p less than or equal to 1. Okay, so if p is bigger than 1, it converges. If p is less than or equal to 1, it diverges. Okay, let's do a proof of this. Let's do a proof of this test here. Okay, so let's take the integral from 1 to infinity of 1 over x to the p power. Okay, and let's see what happens here. So this is equal to the integral from 1 to infinity of x to the negative p. Oh, there should be a dx here, sorry. Negative p. Okay, so now what am I going to do? Well, I'm going to integrate, which tells me that I'm going to take this and I'm going to add 1 to the power. So that's x to the negative p plus 1 all over negative p plus 1. And then divide by that power. Okay. And that's going to be the limit as t goes to infinity of 1 to t. Okay. Okay. And we integrated on x, not p, so keep that in mind. Okay, so I'm going to rewrite this, okay, as the limit as t goes to infinity of t to the negative p plus 1 over negative p plus 1 minus, okay, now I got to plug in 1 to the negative p plus 1 over negative p plus 1. Okay. Okay. So what I'm going to do for the first term is I'm going to factor out a negative. Okay. I'm going to factor out a negative from this guy here. Let me highlight where I'm factoring out the negative from, just so y'all can tell. Oops. Okay, so I'm going to factor out the negative from here. Okay, so hopefully that's going to help. Okay, so let's do that. That's the limit as t goes to infinity of t to the negative p minus 1, okay, all over negative p plus 1. Okay. Okay. Okay, and then this over here, this just becomes 1 to the negative p plus 1, which is 1. This is the minus. And I'm going to, again, I'm going to factor out a negative. I'm going to factor out the negative here. And that's going to give me a negative of p minus 1. Okay, cool. Coolness. Nice, nicely done. Okay, so now what I'm going to do is I'm going to say the limit as t goes to infinity of, now this has a negative in front. I'm going to drop that down and it's going to become a positive. Okay, so this becomes, okay, 1 over negative p plus 1 times t to the p minus 1 power. Okay. Okay. Okay, and then this is going to be plus 1 over p minus 1. Okay, now, if if this p minus 1 here, if p minus 1 is positive, then the limit as t goes to infinity, okay, if that's a positive exponent, okay, then I know that t is in the denominator. And when I put infinity, I get 1 over infinity. Then this limit of 1 over negative p plus 1, t to the p minus 1, that equals 0. Okay, and so thus converging to 1 over p minus 1. Okay, so this converges to a value. Okay, we're using the integral test to say, hey, if this is a positive, okay, in the denominator, okay, that's a positive exponent, then this thing, the limit will go to 0 and it converges to this guy here. Okay, and therefore the original series was convergent. Okay, so that's if p minus 1 is greater than 0. Well, how do I rewrite p minus 1 is greater than 0? So p minus 1 greater than 0 is the same as p greater than 1. Okay, so if p is greater than 1, then it converges. Okay, therefore, the summation n equals 1 to infinity of 1 over x to the p power converges by the integral test for p greater than 1. Otherwise, it diverges. Okay, why? Why would this thing diverge? Well, if this thing was negative, okay, if p minus 1 was negative, let's say that we go back to this step here. If p minus 1 was negative, then this t would stay on the top, and I would just end up with infinity, okay, on the top. I would, because two negatives would make a positive, and I would just end up with t. And when I plug this infinity in for t, the t would stay on top, and that would be infinity. So this thing would just go to infinity, and it would diverge. Okay. So otherwise it diverges, okay, for p less than or equal to 1. Okay, so this is a proof of the p series. Okay, using the integral test. We use the integral test to prove p series. Okay, so what was p series? It was back here. Okay, the p series, okay, 1 over np. Oh, this should be np, I'm sorry. np. 1 over np converges for p greater than 1 and is divergent for n is less than or equal to 1. So again, we could say, hey, you know what? Okay, the summation n equals 1 to infinity of 1 over n squared. What do we know is going to happen to this thing? This thing is convergent. P series, since 2 is greater than 1. Okay, we automatically know that that thing is going to converge. Okay, notice that if p equals 1, what series do I get? Notice that if p equals 1, we get 1 over n to the first, which is 1 over n. And what series is that? What do we call that series? Okay, it's the harmonic series. Okay, this is the harmonic series. Okay, and what do we know about the harmonic series? Does it converge or diverge? Okay, yeah, it diverges. Okay. 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 Another way that you could prove that the harmonic series is divergent, look at the integral test here. What's the integral of 1 over x? Okay. Somebody needs to answer. What's the integral of 1 over x?
ln x.
Yeah, thank you, Ishmi. Okay, this is ln x from 1 to infinity, right? Okay, but what do we know about the natural log as x tends to infinity? The limit as t goes to infinity of ln of t minus ln of 1. Okay, this thing, the natural log function looks like this, and it goes off to infinity. Okay, so this thing diverges. This thing will tend to infinity, and it will diverge. This thing goes to 0, but this thing goes to infinity. It tends to infinity, so it diverges. So we've proven 3 different ways, okay, that the harmonic series diverges. You should not get that question wrong on the exam. We've proven it using, some algebraic manipulation of the series. We've proven it with a p series, and we've proven it with the integral test now. Okay, okay, number 3. I think we're on number 3, right? Pretty sure. Yes. Okay, number 3. Okay, determine if the series, sorry, summation n equals 1 to infinity of the natural log of n over n converges or diverges. Converges or diverges. Okay, so the integral from 1 to infinity of the natural log of x over x dx. Let's do a u sub on ln x. Du is 1 over x dx. Okay, so this becomes okay, integral from 1 to infinity. I'm going to go back to x at the very end, so I'm not going to change my limits of integration. I'll go back to my x variable at the end. So, okay, so the limits of integration here, okay, I'll keep as 1 to infinity. I am going to do a u sub here. So this is u du. Okay. So this becomes u squared over 2. Okay, from 1 to infinity. But again, I'm going to go back to what u was. U was natural log of x. Okay, so this is from 1 to infinity, but you really can't have an infinite limit. So let's plug in a dummy variable, t. Okay, so the limit as t goes to infinity of the natural log of t squared. I'll just go like this first. So natural log of x squared over 2 from 1 to t. Okay, so the limit as t goes to infinity of the natural log of t squared over 2 minus the natural log of 1 squared over 2. Okay, equals infinity. So, okay, this diverges. It's divergent. Therefore, the summation n equals 1 to infinity of the natural log of n over n is divergent. Okay, remainder estimate for the integral test. Okay, so the remainder estimate for the integral test. What does that? Okay, suppose f of k is equal to a sub k, where f is continuous, or is a continuous positive decreasing function for x is greater than or equal to n, and the summation a sub n is convergent. Okay, so we already know that a sub k is continuous and that the summation of a sub n converges. We know that we're dealing with a convergent series. Okay, it's continuous, it's positive, and it's a decreasing function. Okay, so this function decreases. Okay, if r sub n is equal to the summation of the series minus the nth partial sum, this is the sum up to the nth value. Okay, then the integral from n plus 1 to infinity of f of x dx is less than or equal to the remainder, which is less than or equal to the integral from n to infinity of f of x dx. Okay, so what the heck does this mean? Okay, so if we have our partial sums, right? We have S1, S2, S3, okay, all the way to S sub n, okay? And then there's going to be some extra after S sub n. And eventually, as this thing goes to infinity, we're going to hit some S. Okay, it's going to converge to some S. We're going to keep adding these terms, A1 plus A2, A1 plus A2 plus A3. This is going to be A1 plus A2 plus A3 plus dot, dot, dot. plus a sub n, and then this s is a1 plus a2 plus a3 plus dot 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 plus a sub n plus dot dot dot, and it just goes on forever. Okay, that's the true sum of the series. Think of a geometric series that has a true sum. Okay, these terms go on forever. We can find the sum of that series. Okay, and so this series converges. Well, we're saying that the difference between these two, s minus s of n, we're calling the remainder. Okay, so we go all the way out to this one. We want to know, basically, we want to know how close is how good is our approximation of our partial sum, okay, of the sum of the series. How good is this approximation? Okay, because I have all these extra terms here that go off to infinity, but I want to know, well, how much do those extra terms really matter? How much are they affecting my sum? Okay, because eventually they're not going to affect it much at all. Okay, but I can use this to find the remainder. Okay, that remainder value. Okay, or what we would call the error. Okay, so R sub n you can think of as the remainder or the error in the difference between our partial sums. I don't know if that is spelled correctly. Between S sub n and S. Okay, so that's R sub n. Okay. Okay, so we're saying that we can find that how close of an estimate we have, or the error, by taking the integrals. Okay, from n plus 1 on the f of x side, and on the lower side, and then n on the upper side. Now, why would it be n plus 1 would be on the lower? Because if we have a decreasing function, then think about the tail. Okay, we're going to cut this off at n, and then we're going to cut this off at n plus 1, right? Which would have the largest integral from here on out? Well, n would have the larger integral. We cut it off at n, then we still have everything past n. Okay, but then if we cut it off at n plus 1, we're going to have a smaller value. We'd have a smaller integral. Because again, the integral is the area under the curve here, right? Okay, as we go that way. Okay, so that it does make sense that n plus 1 comes first, because that's going to give us the smaller value. Okay, and we're saying that the remainder of the series is between these two. Okay, so number 4, estimate the error in approximating the summation of n equals 1 to infinity of 1 over n cubed okay, 1 over n cubed by taking S10 we're going to go out 10 terms, S10 as its approximation. Okay, so I want to know what's the error on this thing. Okay. So let's see, what is S10? S10 is going to be, does this converge, by the way? Does this 1 over n cubed converge? Okay, is it going to converge to some value? Yes, because this is a p series of p equaling 3, which is greater than 1. So it does converge. Okay, are the terms decreasing? Yes, they are. Okay, and so we're set up, okay, that we can find a remainder on this. Okay, so S10 is equal to 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed plus 1 over 5 cubed plus 1 over 6 cubed plus 1 over 7 cubed plus 1 over 8 cubed plus 1 over 9 cubed plus 1 over 10 cubed. And I think if I plug this into the calculator, okay, I get 1.1975. Let me just verify that. One over. Yeah, 1.1975. Perfect. Okay, so that's S10. Okay, we want to know how good of an approximation is this? How accurate of an approximation? So let's look at the remainder here. So we want n plus 1. Okay, the integral of n plus 1. Okay, that's 11. The integral of 11 to infinity of 1 over x cubed dx is less than or equal to r sub 10, which is less than or equal to the integral from 10 to infinity, okay, of 1 over x cubed dx. Okay, so we really only care about the upper bound here, okay, okay, not necessarily the lower bound, okay, because we want the boundary to be the highest value. Okay, so I'm just going to do this integration. So this is integral from 10 to infinity of x to the negative 3 dx. Add 1 to that, that's negative 2, divide. So we get negative 1/2 x to the negative 2. Okay, evaluated from 10 to infinity. Okay, that's the limit as t goes to infinity of negative 1/2 of x to the negative 2 from t to 10. So this becomes the limit as t goes to infinity of negative 1 over 2x squared. Okay, well, if I plug in the t, it'll be negative 1 over 2t squared minus negative 1 over 2 times 10 squared. Okay, this thing goes to 0 because this 1 over infinity. This is going to be plus 1 over 200, so this is 1 over 200. Okay, which is equal to 0.005. Okay, so the error on this function, this 1 over x cubed function, okay, the error on S10, I should say, on S10 equaling 1.1975 is at most 0.005. Okay. Okay, so let's look at let's look at this guy here real quick. Okay, if we have this n plus 1 to infinity of f of x dx is less than or equal to Rn, okay, is less than or equal to the integral n to infinity of f of x dx. Well, what is Rn? Well, Rn is s minus Sn. Okay, so this is s minus s sub n. Okay, and so if I rewrite this, and I add s sub n to all of these, add an s sub n, we can get an approximation for the boundary for what the actual sum would be. Okay, if I said, hey, I want to know, well, what is the approximate sum for this series, n equals 1 to infinity of 1 over x cubed, right? I would be like, oh, okay, well, what's the approximate sum? Okay, what's the approximate sum of that? Right? Then I could find an upper and lower boundary if I knew what s sub n was, and then I found the integrals of n plus 1 to infinity of f of x dx. Well, that's less than or equal to this the true sum. Okay, because these are going to cancel out, and then this will be s of n plus. So this gives us an approximate value, okay, or a boundary between where to look for our true sum. Okay, this is n to infinity of f of x dx. How this would look in the previous problem? Okay, well, we already know what s sub 10 is. We didn't find 11 to infinity of f of x, but f of x was 1 over x cubed dx. We already did that. We would just have to plug in 11 instead of 10 at the very end there. And that would be 1 over 242. Okay, instead of 1 over 100, it would be 1 over 242. This is 1.1975 plus that thing is less than or equal to s, right? Less than or equal to s, which is less than or equal to s sub 10, plus the integral, and that we found was 0.005 or 1 over 200, 10 to infinity of 1 over x cubed dx. So this becomes 1.1975 plus 1 over 200. If we plug those values into our calculator, okay, plus 1 divided by 242, okay, I get 1.20166 is less than or equal to s, which is less than or equal to, and I'm going to add this one, 1.1975 plus 0.005, okay, is 1.2025. So we know that the true sum of this, we don't really know what it is, but we can get to whatever decimal place accuracy we want by taking higher and higher values of partial sums and then doing these integrals. We could really hone in on what that true sum is. We know it converges. Now we have a way to get an approximate value for a convergent sequence, or sorry, convergent series. Okay, so we know that it's somewhere between these two. We've locked in 1.20. It looks like it's between 0.16 and 0.25. Okay, so 66 and 250. So we can get pretty accurate even after just 10 terms. Okay, again, I don't know what this converges to off the top of my head, but it's going to converge to some value between those values. Okay. Okay, and that is section 6.3. I'm sorry, 5.3.